Thank you very much to everyone. Let me start the backwards order like last time. Yesterday, in the end, I was asking who you were and a few words about my students. I think I would like to start at the beginning. So I recognize some faces, and I'm happy that people are coming back. I'm also happy that people brought back. There is a book that I'm writing, which I have friendly people made a printout for me. So that should contain much more than I'm ever able to say. I will talk, among other things, about the Mannerlot set. And this is the first, let me advertise a bit. It's the first book ever that really tells you the story about the Mannerlot set. It's an old set, quite a bit is known, but no book exists yet, and I want to change that. Okay, we will get there. But, so I remember of yesterday 1.5 names. So let me see. Catalini? Klim. Yes. Well, what you said yesterday. First, that makes it harder. So this is, I also will say something different from yesterday, so it's only fair. So first year masters. Ruslan, also first year master? Yes. Okay. Vadim, PhD student. First year PhD in probability. Yeah, process. Yeah. And you are?
Jura, second year masters.
And you were there yesterday or not?
Yes, I was. Yes.
But before, you left before I asked what were the names.
Ivan, third year bachelor. Yes.
Yeah.
The same third year bachelor, Petro.
Yes, mate. I'm Sviatoslav.
You were there yesterday also?
Yes.
You were not?
No.
Unfortunately, I was not able, my transport was...
That's fine yesterday.
Yeah.
So, you did a good job by bringing them along.
Yeah.
So, you were there yesterday?
I was, yes.
Yeah.
Second year
Bachelor. Okay. So then you should move. You should come here. So you know my grading scheme. First row gets an A, the second row gets an B, then comes the C. No, that's not. You won't get a better grade. Okay. So my plan for today. Actually, I don't have a plan. I want to adjust to what questions you have and what we should discuss. But what I was planning anyway was to discuss whatever complex variables is necessary to understand what's going on. And so I will be looking specifically at you to make sure, apologies. That's actually what I usually do. Can you do me a favor? Start a piece of paper. No, you start because and then just go around, write all your names. So that's what I do in all my teaching. That's the best way to learn names. So, complex variables. You know what complex numbers are. And you know they're a field. Addition, you know the complex plane. You know the Riemann sphere. You know the Riemann sphere. Okay, you know what a holomorphic function is. Complex differentiable. Well, the holomorphic is not homeomorphic or so. Holomorphic. Okay, then how about the third year people?
We know it.
Okay, so then apologize for some repetition, but we should bring everyone to speed. And that's in principle. Let me start with the Riemann sphere, which has different names. A priori it's all the same thing. As a set, it's the complex plane with a single point at infinity added. And the intuition, I always do something intuitive. If you don't understand it, I cannot work with it. You know stereographic projection. So here's the North Pole and on the sphere, and then there is you can take any point on the sphere, you connect by a straight line to some point in the plane. You've seen that? And that shows that the sphere is homomorphic to the complex plane. Well, you have to remove the north pole. If you remove the north pole, then for every point, there is a straight line which will eventually intersect. And that way, you get a homomorphism like this. When you change the point continuously, the image will change continuously. Right? So, then, now we say, we add a point, so and when our points here go to the north pole, then the connecting line will get ever more horizontal, and the image is converged to infinity. So the north pole corresponds to that point at infinity. Okay? So the sphere, the Riemann sphere, is nothing but the complex plane with a point at infinity. It's a very natural thing to look. First, give it a name Riemann. He is dead also. The Riemann sphere is that. And the next thing, holomorphic functions. So you have a map F from the complex plane to itself, which you can write f of x, y is, well, little f of x, so this is the complex number. This is the real part plus I times the imaginary part. So this goes from C, so far C is the same thing as R2. Well, you know that a map is differentiable by definition if it can be approximated well by a linear map. That's the idea of differentiability. And for maps from R2 or from C to C, the derivative is a matrix, so that the derivative at the origin is the matrix A, B, C, D. You have a map from R2 to R2. The derivative should be a linear map from R to R2. So it's a matrix like this. And it should be a complex linear map. Complex linear map should be a multiplication by some number, and need a new number, by a complex number. You know the geometry multiplication by a complex number, what this looks like.
And then about this.
So that can be a rotation and a stretch. So it is, you can write a complex number as r times e to the I phi. E to the I phi is the rotation, r is the real scaling factor. If you write e to the I phi as a matrix, it's something like cosine phi, sine phi minus sine phi, cosine phi. That's a rotation bit. So this guy should, if the linear approximation is like a complex map, it should have the form r cosine phi r here times then sine phi minus sine phi and cosine phi. That's the necessary condition so that f is complex differentiable at the origin. Okay? So if you stare at this, these two entries should be the same. So it's equivalent to A equals D, and these should be the same up to sine. B equals minus D.
Minus C.
C. You see, this is when you teach, you should always introduce a few errors to check whether people are awake. Okay? So, and it's easy to check if you have this condition, you can pull out a factor of R So that's the rotation matrix. So this is equivalent. And then F is C differentiable everywhere. When for all Z in the, we have to get used points in the complex plane are called Z not X. That really means df dx equals dg dy and df dy equals minus dg dx. df dx is this thing, df dy is that. So this is a French-German collaboration. It's called, at least for us, the Cauchy-Riemann differential equations. And like so often, the Russians developed it earlier and have a different name for it. Maybe they have a different name sometimes when they didn't discover it earlier.
Has everyone signed this paper?
Thank you. Okay. So that is, if you write a map from the plane to the plane, even when it's differentiable, that is a very strong condition. And it's, you could say every strong condition is very special, a great restriction. But it keeps all the interesting functions. So this is called a holomorphic function by definition. It's complex differentiable on an open set. The detail. So functions that are, let's say, everywhere complex differentiable. In some sense it's special, but it's a powerful theory. And all the functions, well, that you can write, this is that you can write them always. They always, for instance, have a powered series expansion. So over the complex, f of z is the sum a n z to the n for some coefficients. At least when these are global maps. And you get all the polynomials, you get all rational functions, you get sine and cosine. And so pretty much all the functions you know and you can think of are there. Okay? So, our third year friends, all known to you? Okay. Then, what do you think of the Riemann mapping theorem?
What?
The Riemann mapping theorem. It continues surjection from the circle to the boundary of the Mandelbrot set. Right, so then there's already at least the boundaries then path connected. And to get to the interior is not very hard.
Well, it seems that then the complement should be simply connected, and then the complement and the Riemann sphere, the complement is connected, or the simply connected is connected.
Well, simply connected makes only sense when you have open sets. And the Mandelbrot set is not open.
Yeah, I mean the complement.
The complement is holomorphic to the disk. So, on the disk you know everything you want to know. Okay? So maybe I should now give you a definition of the Mandelbrot set. Who of you thinks you know a definition? At least half the people know half a definition. Who has never seen a definition? Okay, then I think it's just about time. But you've recognized the picture, right? So, there are, shouldn't have given this, the Riemann mapping theorem. So, the definition of all points C in the complex is all similar. C in the complex plane. So that the sequence C naught is 0, and then Cn plus 1 is Cn squared plus C. So, it all depends on a blue C, and we have this same C. Start with 0, whether this sequence is bounded. So let's see some exercises, some examples. C equals 0. Is it in the Mandelbrot set or not?
Yes.
You said yes, and you also said yes. I wanted to start with you because you're the youngest. Okay, so that is in the Mandelbrot set. The sequence is just 0, 0. Yes. 1. I want to hear an answer from everyone. I want to hear an answer from everyone. You were quick with the first, and now we'll give the others a chance. Okay?
Second, because it's not bounded.
So what are the first few terms of the series?
Please repeat.
Can you calculate for us the first few terms?
1, 2, 5. Yes, no.
Yeah?
1, 5, 9.
What? After 5 comes?
26.
26, right. So, it's not in M. What about minus 1?
Not in M.
Not in M. Yes, yes. Should give the students a chance.
In M.
Hmm?
In M.
It's in M, and the sequence is
0 minus 1, 0 minus 1.
it's oscillate. Right? Last example, C equals minus 2. And the sequence is?
Minus 2, then 2, and then 2.
It says 2. Alright, so let me draw the Mandelbrot set again. Something like this. 0 is the center here. Minus 1 is here. Minus 2 is the very end point. And then somewhere up here is the point I. That's kind of in the end of the filament. This point is the point 1/4. And to the right of it, 1/4 plus epsilon. You're outside of that. Okay. So the point 1 is about here. Now let me make a little excursion, because I've just been working on it. So, I take the point C equals 1/4 plus epsilon. In fact, a little exercise is if some Cn is bigger than 2, then the sequence Cn goes to infinity, so we are not in the Mandelbrot set. And that's easy to check. So I want to show that when you have 1/4 plus epsilon, then it will go to infinity. So I define a quantity n of epsilon, which is the number of iterations until Cn is greater than 2. I claim that we are 1/4 plus epsilon here outside of the Mandelbrot set. So after some time it will be bigger than 2. The sequence is unbounded. Okay? So then we can make some computations. I don't memorize the numbers exactly, but in principle, one can make experiments 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, something like this. And somehow the number of iterations here, you need something like 3 iterations, give or take. Then here you need 31.
I see where you go.
You see, so this is 314. You can predict the next one.
31,450.
Maybe 16 actually.
No, okay.
Yeah, it's... So, and that's true. So in fact, a theorem, I don't memorize the number exactly. This number n of epsilon is, what should it be? Root epsilon to the minus 1/2 times pi, I think plus O of 1. Something like this.
In this table we have, so the first column is epsilon.
Oh, this is the epsilon, yes.
And from which part of mathematics does E come from?
Let me tell you a story. I like stories. And that's just, the book is full of stories also. That was observed by many people over the years. And in fact, you can try the same thing here. This is the point minus 0.75. So you have Cn equals minus 0.75 plus I epsilon. And you want to ask whether, it's an open question, this line intersects the Mandelbrot set at a point other than at epsilon equals 0. And here n of epsilon.
It's an open question whether there are any.
It's still an open question for this easy straight line. I think if you really wanted to do hard, you can prove it. So here is epsilon to the minus 1 times the same pi plus O of 1. So there's no square root here, but other than that, it's the same. And that's how people discovered it in the 70s, even before the Mandelbrot set was defined. They discovered that they wanted to see whether the line intersects, and they made the same observation 50 years ago. And over time, various people have given some sort of proof with more of different precision, but none of them give an explanation. So you see something, oh yes, so somewhere you have to use transcendental functions, and somewhere there is a sine function. When you have a sine, then pi shouldn't be far away. Is that convincing? So that was the story, but it was known. And then 2 or 3 years ago, a first year undergraduate, maybe second year, let me say second year because the story is nicer, talks to me and says, have you heard of this? That you get pi here and there. And I told them I had heard about it when I was a PhD student. And Yeah, so people seem to have heard about it. And there are various proofs floating around in the world. But nobody had an explanation. And then we sat down and we come up with an explanation, which is maybe it's not the part of today, but there is a conceptual reason. And the reason why it's pi is because the circle here has diameter, it has circumference 2 pi. And you divide by 2, which is the degree of the polynomials. There's an explanation as simple as that. But it required 50 years for the problem to be sitting around. And then for a smart student to ask me and for us to sit down about it.
Does it work there?
Yes, it's all the same. And it works on countably many other points in the month. Pretty much all the interesting points. It works also.
Which points are interesting? Those that are...
Those for which it works.
Those that are connected.
We're getting a bit carried away. But let me ask a different question. Who of you know the videos by 3 Blue 1 Brown?
Of course.
Of course. So, I'm in email correspondence with the producer of 3 Blue 1 Brown, and he wants to make a video about this. We are working on this. Yes.
You will be waiting.
Yes. And I hope not for too long. I owe him an email answer with...
Take your time.
Yes. But speaking of 3 Blue 1 Brown, you know there are videos on the Mandelbrot set. Have you seen this? In fact, there are 2 videos. And also root finding. Some of what I'm talking, so you've seen the videos. So there was the first video at some point, and then soon after they produced the second video, saying, oh, there is much more than we thought was ever true, so we had to make a second video. Special thanks go to Sergei Shemyakov of Aix-Marseille University, who told us about it. And that Sergei was a PhD student of mine, who contacted them. So there already is a video, not written, but kind of encouraged and explained by my PhD student. I made a video. So when you check it, find Sergei. So I'm happy to have it. It's not the student talking here. It's a different student, Sergei Shemyakov. He finished his PhD meanwhile. But he's behind one of those videos. You can find it online. Yeah, I can. Should I skip ahead and talk a little bit about why this is true? I mean, I promised some connections, and it's nice to make some plans, but when there are discussions, can you follow?
Yes, I hope so. There are a lot of information, but it's general concepts, yes.
You have the book next to you. So let me tell you. So where's the eraser? Here. Okay, why not? Now let me do something which I was trying to do anyway. On the Mandelbrot, there are this domain here. It's called the main cardioid. And this is the interior is exactly the set of points C in the Mandelbrot set, even the complex plane, so that the sequence Cn converges to a fixed point. A priori, we've just required that the sequence is bounded. And there are many ways of being bounded. For 0, the sequence is fixed. For -1, it hops between 2 points. For -2, it starts at -2 and then goes to a fixed point. At I, it starts at 1 point, then jumps between 2 other points. If you start at 1/2, it will converge towards, now if you start at 1/4, then you have the map. Have you seen a cobweb diagram? Something like this. Continue until we get orders from you.
Well, we should go to shelter.
Continuing
the shelter.
We should read.
Let's check which shelter.
So, for the record, folks, I really appreciate your endurance, and I wish you all the strength to get through this. Yeah, I admire your strength. Keep strong. Slava Ukraini. What can I say? Yes. Okay. So, one day we should keep drawing little mammals all over the place. Okay. So, we have the sequence Cn, very good, and this is a bit old. So, Cn is bounded when you're in the Mandelbrot set. It can, one possibility, it can converge to a fixed point if and only if this original C is in what I call H1, it's this guy here. Okay? So, and that is, what is this? There is a map, mu from H1. Somebody was asking me about the Riemann mapping theorem applied to this guy. Was it you? So, this is bounded and open and connected and without holes. So, there's a Riemann map given by the parameter C goes to C over 2 minus C over 2 squared.
That's a question. Didn't we have that for minus 2? It also converges to some point. Do you mean that it is like the same point for...
You're right. You're right. So I haven't defined what an attracting fixed point is. Since an attracting fixed point, which means you have a fixed point in nearby orbits, all converge there. So at -2, so this is attracting, at -2 happens to be a fixed point also, as we know. So you have -2, but when you have a nearby point, it will drift away. So in order to stay, you really have to hit it on the nose. So this is an open set. And then for every number of iterations, there are countably many more points until you hit a fixed point. They exist, and they're interesting in their own way. But really, yeah, you're right, and I should be more precise. Well, I should not, and then you should ask good questions.
So which one is like a stable region?
Exactly. So there is a very explicit Riemann map. And we can compute it when, no, is it the other way? C equals mu over 2 minus mu over 2 squared. And so when mu is 1, you have 1/2 minus a quarter. You land at the point 1/4 that I mentioned earlier. And when mu is -1, you have minus 1/2 minus a quarter, then you get to the point minus 3/4. Okay? But this is something we can compute, and this is an easy exercise. This is really an easy exercise. Just the hardest part is calculating the derivative of a quadratic polynomial. And for the young people, you do it the same way you do it for real maps. So the derivative of z squared, the derivative with respect to z of z squared plus c is simply 2z. And that's the 2 that turns the 2 pi into pi. Okay? And then the second possibility, the CN can converge to a 2-cycle. It doesn't converge to a fixed point, but it does every other time it does it. So the even ones converge to one point, the odd ones converge to another. Okay? And that happens here, CNH2, in this thing. And there's a Riemann map also. In this case, C equals -1 plus mu over 4. So you start with the unit disk. You divide by 4, that means you have a disk of radius 1/4. And then you translate it and you get this guy, which means this thing in the manifold set, which looks like a circle, actually is a circle. It's a perfect circle. Okay? So this is an easy exercise. This is an almost easy exercise.
It cycles on itself, right?
That's the point of a 2-cycle.
No. The points of the sequence Cn can travel
Can they jump between different parts of the
For every point here on the disk, there is a 2-cycle. And then this sequence that we mentioned.
No, but the second point of the cycle will be also in the disk, right?
No, I'm not saying, even for the fixed points here, when you have C equals 1/4, then the sequence converges to 1/2. So the seed here, that's the base point. That is wherever it is, but the sequence will have absolute value less than 2 somewhere. Okay? And I want somebody to take a picture from the back there, because this is the room and the people. From the very back. Yes. Okay, so just do a few and they'll not pay attention. Got the point? And then you can ask the question, what about period 3? Well, then you get 3 domains. One is to start at a little Mandelbrot set here, around -1.75488 something, algebraic number of degree 3. And then there is period 3 here and period 3 here.
Oh, and then you have cycles of all sides.
Right, right. And you can compute the numbers. Period 4, there should be 6. 1, 2, 3. 4 is around -1.91 or so. And then there is 1 up here and the symmetric 1 down here.
whole subject in itself, Mandelbrot topography.
Right, and we will get there. So my plan is to first, afterwards, the plan is to first tell you how complicated it is, and then I want to give you a very simple description, a surprisingly remarkably simple description, that all the complicated stories can be produced in a very simple one line. I mean, the definition was simple, but the set itself is very simple also. So like with the Riemann map, it's much simpler than you would have thought.
Each one is an open set?
Yeah, and on the, so I talk about the open set. What happens on the boundary? For some of the boundary points, there's a countable dense set of boundary points for which you also converge to a fixed point, like 1/4, for instance. And then there are 2 more possibilities. Siegel and Kramer, which is a long story, but we should have time till tomorrow. It's cozy, it's getting warm. But this is getting very difficult. And some of these questions were due for Phil's middle to your course. So we can get there too. In any case, so for every period you get something. For period 3, it is a challenge but possible to write simple formulas for the Riemann map, explicit formulas. It's harder, and you have to know something, and you can do it.
Because we have this complex set, more complicated set near that algebraic function, right? Not the circling.
We're getting into algebra, yes. And for period 4, it's very difficult. And for period 5 and higher, there is Galois theory. It tells you there cannot be, right? So this is algebra at work, and you get to see it here. Okay, but I'm not good at keeping time with the nice and interested students here. So let me conclude with the story of pi. So let's compute z squared. That's a polynomial that depends on the parameter c. Actually, let's answer this question here. The first one. So the fixed points z squared plus c equals z. Then you have, well, the quadratic polynomial has 2 fixed points. Okay. Good. Fuck you, Putin. I have to focus. So back to fixed points. So midnight formula. Remember what that was? You weren't at my class yesterday, so I should ask, what was the midnight formula?
Quadratic equation.
And why is it called midnight formula?
Because we're supposed to remember it even at midnight.
Well, this is a joke in German high schools. The teacher tells the students, and even if I wake you up at midnight, and the students say, at midnight I knew it, but in the morning at 10, I don't. So, that is something like -1. Something like this.
But it should be plus 1/2.
And fast, what that means. Not midnight. And now, how can we check whether the fixed point is attracting? We compute the derivative, p prime at z. You see, when you're near the point, here's a fixed point. And then, well, p of z plus epsilon is p of z plus epsilon times p prime of z plus higher order terms. Complex differentiable means it can be approximated well by a linear map. So, and this is closer, at least when epsilon is small. So the fixed point is attracting if and only if p prime of z is less than 1, which we call mu. Right? So, then we are on the boundary, and this is a very interesting story. And that comes to the day when I talk about the stability of the solar system and everything else. Then not now. I want to get to pi. Let me see whether I can compute this. It's an easy calculation. So p prime of z is 2z. And z for the fixed point is, and this I call mu. Right, that's the derivative, and I want to check whether it's bigger or smaller than And now I want to eliminate this Z. I just wanted, so what do we, well, we do it together. So, as I said, I prepared something else. We have two equations. Z squared plus C is Z, and 2Z equals mu. Right? Eliminate Z from this. Well, that's easy. Z is mu over 2, which is what we are hoping for here. So C equals Z minus Z squared, which is mu over 2 minus mu over 2 squared. It wasn't so hard, was it? So, if mu, the derivative, is less than 1 in absolute value, we land at this domain. And now there is a theorem. I have to get to this. There is an attracting fixed point. But just because there exists an attracting fixed point, why does the sequence converge to it? It's a theorem. We get there.
We got this formula for mapping.
Right. So this is the proof under the condition that if there is an attracting fixed point, the sequence will converge to it. That's not obvious.
Do we use the fact that this map contracts?
With respect to which metric? Often we have to find a good metric. Now here is, so our polynomial, where is it? Here. What are the critical points of this polynomial? Yes?
Minus 3 over 2.
No, what's the critical point?
0.
0. Critical points are the zeros of the derivative. The derivative is 2z, and the only solution is 0. So, and the theorem that I'm using is that if there exists an attracting fixed point or attracting periodic point, then one of the critical points of our map must converge to it. And there's only one fixed point, which is 0. So if there exists a fixed point, an attracting fixed point, the only critical point, which is 0, must converge there. So that completes the proof, using something else. Can you still follow? Roughly. Very good. Okay, so the exercise for this thing is in principle the same thing, except you have to go to the second iterate. You want to get fixed points of the second iterate. So, Z squared plus C squared plus Z equals Z. Now you get 4 solutions. Right? But 2 of those solutions are already the ones that we had before. Fixed points are also fixed points of the second iterate. So you divide them out, and what's left is another quadratic equation, which only has the 2 cycles as solution. And you do the same thing. Okay?
Can we calculate the number of the fixed points for any n by recursion?
Yes.
Do they ever...
You tell me tomorrow.
Okay. Do they ever... does this polynomial have double roots sometimes?
Ah. Think about it. There is an elegant argument for this question using 2-adic numbers. So you're asking about connections. So you keep asking the right questions to find the connections. So the answer is yes, the roots are simple. And this is actually some of the polynomials with which we produce the world record for fast risk landing. All the roots are simple, and it's 2-adic evaluation. Let's see whether you get there. But I want to, somewhere I should stop. I want to tell you where the pi is coming from. And as I said, it doesn't happen very often that there is a 50-year-old statement about the minor roots that everybody has known. And there are so many kind of proofs. And it's taken 50 years until there was a conceptual explanation. And just last night, so we're writing a paper for the 3 blue 1 brown. Just last night, one of my students, the one who asked the questions, sent me a continuation of the draft, and while I was speaking to the other student who's working on it. So this is really very much in the making. So you see, I appreciate students who ask questions. Let's see what happens. I cannot promise you a video, but you never know what happens, and that's research. So let me draw so you know the cobweb diagram. You have a quadratic polynomial, and this is the f of x equals x. You start with some point x, then here is x, this is f of x. And then if you go here, then this is on the diagonal, y equals x. So that means here you have y, and the y has become the new x. And you can iterate this again. Maybe let me start here. So you have some x, this is f of x. You make it the same, so f of x equals y. At this point, the new x has the same value as x. So you go down here, and that way you iterate. You see that? And you see here the derivative is bigger than 1. So when you start nearby, you will quickly disappear. And if you have a fixed point, which is attracting, you converge to the fixed point. So that's the way to see geometrically why attracting fixed point wants to have that property. I didn't draw it too well. Should I draw it again? And now this point 1/4 is very special because this is the unique map. So here is 1/2 for which the map, the graph just touches. I promise 2 fixed points, but if C is a quarter, these 2 fixed points are the same. So if C is less than that, you have 2 real fixed points. If C is bigger than 1, you have a pair of complex conjugate fixed points. We will read them in a moment. And for C equal to 1/4, the iteration looks like this. So this is a boundary point where you still converge to a fixed point. One of the countably many for which this is the case. And now are people with me so far? Now let me use some, now there are not so many other colors.
When, like 1 hour lectures, how much time do you can reschedule them for the rest of the week? Like, what's your vision?
No, I'm getting to know the students, they get to know me.
Well, you are mostly speaking here. So how much time do you usually?
I wasn't planning to speak about this pi thing, but then people, so I let it be usually an hour plus a few epsilons.
Okay, up to an hour and a half. Maybe 10 more minutes.
Yeah, right. I mean, that's all you have things to do, and you get homeworks. And,
very busy, actually.
which is good. Yeah. Yeah, okay. But at this moment I don't have a clock, so I don't know where we stand.
We're 17 minutes past.
Okay, so then let me try to just give you an idea.
And just a quick note that I think we still have cookies and tea upstairs.
Oh yes, and we are allowed to go up, yes.
Maybe someone else is drinking.
Well, things happen in life. So, we have the case, we are 1/4 plus epsilon, that's what we're interested in. Right? So then we really have, maybe in black, this is where it escapes, but very slowly. So we still have the 2 fixed points, If we have c equals 1/4 plus epsilon, this is where we stand, then this is 1/2 plus minus root of minus epsilon, which is 1/2 plus minus. These are the two fixed points. Okay, you see the root epsilon coming, and the derivative, there should be a root epsilon here. I promise that I should deliver. And so what does it say? Yes, and now the derivative, mu is 2z. The derivative of z squared plus c. And at the fixed point is just 2 times the fixed point, which is 2 times 1/2 plus minus I root epsilon, which is 1 plus 2I root epsilon. I promise a factor of 2 coming in from the derivative. And that's that. And now, so so let me turn the picture around. This is kind of the real slice. Now we look in the complex plane. And the two fixed points, here is 1/2, are 1/2 plus 2I root epsilon and 1/2 minus 2I root epsilon. Right? And the orbit is kind of on the real line, slowly passing through this. So again, I closed the gate when it can go through. And here what we should use is for 2 coordinates. It turns out that there are actual, asymptotically at least, actual circles, so that every circle maps to the next one. And if you use 1 over z coordinates, change coordinates from what we have here to 1 over z, then this family of circles becomes a family of vertical lines adding +1, and here you have a family of same lines add +1. No, it's just the other way around. Here, when you're here, you want to converge to 0, so in 1 over z coordinates you go to infinity, essentially by those lines. I'm cheating a little bit, and I'm not cheating, but I'm using higher order terms. So there's a family of vertical just translation by 1, and that asymptotically gives us circles. And the idea is we are interested in the orbit here. Adding 1, just shift by 1, you have the orbit here. Now I compare the orbit here with the whole circles. And these circles come in vertically at the fixed point.
Is it 1 over z or 1 over z minus 1/2?
Perhaps. Smart students, yes. Well, I had made an initial coordinate change to move that at 0, which is skipped, and then, yeah. So, I replace the orbit by this family of curves, which is a family like so. Okay? And then when I open the gate, we are here, and here I have to justify something. Here's the orbit that's coming in. I still have, they all end there, circles like so. So I want to count the number of iterations here until they go through. When they go out, they go like this. And the surprise comes, at this point, the tangent line in the circle, it's vertical, and when it goes out, it's still vertical. Right? So you want to rotate the tangent line, the orbit that you're interested in. You see the pi come in? You want to watch the orbit, you compare it by the tangent angles, and this tangent angle has to go through with 2 pi. That is where the pi is coming from. Is that a natural explanation for pi, just a full circle? I haven't finished the proof. But you see why this 2 pi is naturally a number pi. And this is new and unpublished. It's not classical. Young people can produce new mathematics, I keep saying. So the number of iterations for epsilon is 2 pi divided by how much the tangent angle rotates here. That's the argument of 1 plus 2I root epsilon. Maybe I'm ignoring higher order terms. Let me do that. That's the rotation angle. So that is, I hope I'll finish here. What is the argument of a complex number? No tan. No tan or arctan.
Just the angle between the
Yeah. Yeah.
the imaginary real.
Right. And I want to claim that arc of Z is the imaginary part of log Z. Why is that so? If Z is R times e to the I phi, then log Z is log R plus I phi. Right? So the imaginary part is I phi, maybe up to factor I or so. You see that? So this is the imaginary part of log of 1 plus 2I root epsilon. Next thing, what is log of 1 plus Z when Z is small? Not just O. It's Z plus higher order terms, which I'm ignoring. So this is 2 pi divided by imaginary part of 2I root epsilon. Alright, and imaginary, this is 2 pi of 2 root epsilon, and that is pi over root epsilon. Okay? Now is what I claimed. So in some ways, I'm very happy to present to you connections to interesting, deep areas of mathematics somewhere else. But here I have an completely elementary explanation, which was waiting for 50 years until the right students asked the right question to the right person.
How natural it is to consider this circle? Because it doesn't look natural. It looks like magic a bit.
In any case, this was known to Fatou.
Okay.
Yeah, and it's not, I mean, it is an accumulated collection of tools over time. But if you have something near the origin, which is very messy, try 1 over Z coordinates to spread them out. Shouldn't be too surprising.
Naturally translate lines into circles.
Well, that happens afterwards. First you try 1 over Z coordinates. And then if you can do the calculation at such a point easily, at least when the gate is closed. And it just turns out that near the origin, 1 over Z coordinates near infinity, the map is addition plus of 1 plus small perturbation. And it just happens to be plus 1 plus a small error term. When you go out, the error term is small, and then you get asymptotically exact circles here.
By the way, I think we should be accurate with error terms because we count number of iterations and they accumulate on each iteration, right?
No, we just have to. You always have to be careful. Yes, but we just want to have, I mean, if this is you always have plus higher order terms, and you have to check what the higher terms are. So this is...
But this wasn't a proposition. We have this plus O small of 1. Yes, so this is symptotic.
Yeah. That's
not
coming...
exactly the number, but for the first numbers, it turns out to be exactly matching.
Well, I'm not sure. I made up the numbers because I wanted the results, yes? Maybe. Also, why go up to 2? Why not iterate up to 7? And then you get a different constant. So that was the plan. Complex analysis required for dynamics. I hope. Yeah. Okay. And how the pies come out of it. And really, I find it amazing that this has taken 50 years.
It was the most unexpected way to come out for pi, because maybe it's not about like spin with picture, not about coordinates.
Well, but it's, don't you agree? I mean, how can it be more natural? Where's the pi sitting? Did I erase it? Have I erased it? Here, yes. It's about as natural as I can possibly get.
It is.
Yeah.
But it is so unexpected.
There's a video by Numberphile on this pi story. The mini text, and there is a Numberphile video who presents the result. But I have no explanation why this is so. Oh, it's new. And I think this is the second time we're giving a talk about it. There was a school in Barcelona, organized by Kostya Drac and his friends in Barcelona in June, when we presented it first. And this is the second time. So that's very fresh. So, I think this is a good point to stop. Oh yes.